Mr. Brian Gardner right here.
Hey guys, thanks for coming out on Wednesday morning. Not a popular time to be out. So I'll talk about true circuits. In fact, why don't I do this in a little different order? Hope I can go back. So we're one of the older mixed signal IP companies. We've been selling IP since 1998. So in many ways, we kept kind of blazed the trail. Sort of in the older days, and even now, a lot of companies that call themselves IP companies really are more like design services. And that's really where you trace the roots to IP. There were especially big companies. There may be something that they weren't good at, or they didn't have the resources, and they said, hey, we want you to build XYZ. And then they generally specified it, XYZ, blah, 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 exactly what you wanted, and a design service company bought it. And if that IP company were lucky, they would resell it to somebody else. Or maybe they would use it as the foundation to build some other thing that was specified. And then gradually, especially with a lot of interface standards and things like that, IP became a little bit more standardized. Because what you really want as a customer, the reason you come to a third party is to save time and reduce risk. And what you really want to do is buy something that's off the shelf, silicon proven. Maybe it's not exactly what your engineer would have wanted, but it will work. Maybe it's programmable. And that's the kind of thing we try to do. And what I call that a metamorphosis from a sort of a service provider to an IP, or from services to product, right? So you don't want to go down to or probably most people don't want to go down to the car dealership and say, I see you have a car, but let's build one for me. We'll put some different kind of wheels. We'll do the engine different. We'll change things up. And then, of course, you get that car at home and it never runs, or it has lots of problems. You want to go down and you want to get something that they've already built 100,000 of. And that's what we're trying to do at True Circuits. We really want to be a product supplier. So if you go to our website, you look at our product page, you'll scroll through literally hundreds of products, and all of them exist. The reason we have so many is that we also apply a lot of automation to the problem. So we design our IP at kind of a higher level of abstraction so that we can easily port products to different processes, and in fact we can build different varieties of product. So you'll find products there. You'll find products that are robust, really wide range. Sort of in the old days for PLLs, which is one of the things we specialized in, they tended to be designed for one job, maybe one frequency. We build very wide range frequency. We also have a lot of programmability, so you can program them, what the multiplication factor is. You can program the bandwidth. You might want the bandwidth to be high. In generally you would like the control loop to have a high bandwidth. But in some cases, you might want to have a lower bandwidth because you want to filter some jitter out that's downstream in the system. And a lot of times you really don't even know what the optimal settings are until you get the chip. So, many, many times when people get back to silicon, we'll have a meeting with them. They'll try some different, programmable things that aren't obvious, and it'll have a big effect on the jitter or something like that. Because when you put a whole chip together, it's not really easy to tell exactly where all the jitter is, and the sort of third level effects. So that's what we're doing. We figure when you're building an SoC, it's a hard job. It's a big job. It's big. You probably have to buy 50, 75, 100 pieces of IP, as well as design a lot of your own, specific circuits. And that's a hard job. You got all these different specs. You got some interface specs. You got specs that your architect may have built. You may not know exactly what process node you want to standardize on just yet. Maybe you haven't decided whether we're going to spend the money on 16, or even if you're at something like 28 nanometer, there's HP and HP Plus, and maybe TSMC will bring up another variety that has some advantages, or maybe is smaller or faster or lower power. And that may not be stable at the beginning of the project. So you buy all this IP, your operations team is still negotiating the wafer, what wafers you're going to use, and then, we're going to use a little bit different process or a little bit different metal stack, or we're going to have to take out one of those VTs because it's too expensive, and then boom, some of your IP is no longer viable. Some of your IP suppliers come back and say, whoa, this is going to take a little more money and a little more time. We do all that in an automated fashion. So we ask you, what process you want, what process node, what VTs, what metal stack. You might want embedded flash, no problem. We press a button, you got what you want in a single hard macro with the decap, the guard rings, and the keep out all built up. All these things almost always run off core power. So they're really very, very easy to integrate. And that's what we're about. What we want to do is for us to make your job easy. Which got to the next slide. We got you covered. So again, that's what we're trying to do. We're trying to make it easy. Also, you do your next chip. Maybe you migrate from 28 to 16. Maybe you decide to go from TSMC to SMIC. We have the same product, looks the same, integrates the same look and feel, no problem. So, that's good. Once you have some experience with how to use the product, you can keep using it generation after generation, make things easy to do. So, like I said, we use a lot of automation. Our president and the guy that leads our technical team, I think, is giving a talk in one of the ballrooms right now about how we do things, because it's really kind of unique. I mean, if you look at our PLL design, it's not schematics. It's all a lot of C code or code. We code up how the circuit looks. We code things up at a higher level of abstraction. That same coding has layout, or at least layout hints. It has exactly what test bench, what Monte Carlos you want to run. All of that's coded in kind of one unified database, if you will. So that way, if we were to port something to a new process or go from a regular PLL to a spread spectrum PLL, it's almost literally pressing a button. The thing will run, it'll create the design, it will kick off thousands of Monte Carlos. We use a lot of our own tools so that we can connect the tools together in our own way. So we actually have our own version of Berkeley Spice that we've customized over the decades. So we don't have to worry about licenses. So we can kick off thousands of Monte Carlos on 1,000 CPUs and run overnight what might take a week or even weeks. So it doesn't sound like a big deal to have that level of automation, but just a small job of, let's say you come and get a PLL and you want to, okay, you're going to run it in the embedded flash process. Maybe we've never looked at it in the embedded flash process. The small job of assigning an engineer and having them just, double check, run the simulations for the embedded flash can easily take a man-month. To something as simple as that, we can do that in an afternoon. An afternoon of machine time. So an afternoon where the actual engineer can play golf. But we know engineers don't play golf. Sales guys play golf. The other thing that that complements what we do is we have designs that are relatively insensitive to process. So the PLL itself is a self-biased design. So you're basically telling the VCO, okay, I don't know what your process is, but you optimize. You find the optimal point, the optimal place for that setting. And in general, we try to use circuit techniques that are robust. So, in fact, I was in China a few weeks ago. I visited a couple of companies that do Bitcoin or cryptocurrency mining. They needed really low power. I actually sold them a PLL that will run at a gigahertz at 0.55 volts. So that's what they were looking for, something that was, just before the process goes to sleep. We test up to 150, so the process, the IP we have is suitable for automotive applications. And then, anytime you can build circuits that are robust and not that sensitive to process, it makes it easy to port. It makes it easy to keep the customer out of trouble. You know, it means that the analog supply can vary even plus or minus 15%, and things will still work. A lot of times with an analog piece of IP, a great deal of effort has to be done at the customer site trying to keep their lines quiet. It's real easy for us to write on a spec, hey, 2 millivolts of fluctuation. We wrote it on a spec, no problem. But actually trying to build a supply in the real world in your budget is difficult to do. So that automation coupled with proven techniques that make the design robust are the keys to success. So our product line, I talked about PLLs a lot. We have a wide range of PLLs, some PLLs that multiply by a small amount and but are very small and low power, to PLLs that will multiply up to 250,000. So we have an ultra PLL that will take a 32 kilohertz crystal and create a 3.2 gigahertz very low jitter clock, which is kind of amazing. And it can do, it means things like, since it runs at such a low reference frequency, that means that the bandwidth can be very low. So the PLL can completely filter out, say, jitter that might come from a crystal or an oscillator. So you might be able to use this and buy a cheaper oscillator or move from an external oscillator to a crystal, even though you're running a very sensitive SerDes. It also means it offers new ways to manage power. So you have 32 kilohertz. It means you can create an output anywhere between 32 kilohertz and 3 gig. You could even turn off the PLL and still have that 32 kilohertz. 32 is what's in your watch if you have an electric watch, and just have that heartbeat frequency and go into a super low power state but still be able to do something. We also have the DLL, a delay line, which was typically used in the old days for as the heart of a DDR5. And now that people offer hard DDR5s like we do, it's not as popular, but it's regained popularity in the flash interface OMPI. So an OMPI interface looks a lot like a DDR DRAM interface looked like a couple of generations ago. So it'll delay any number of signals in very fine increments. So it can also be used for other chip interfaces, or in some cases you want to align some signals on your chip. And then we announced the DDR5 not long ago. So we've basically taken our entire IP portfolio and we've applied it to the DDR5. So there's multiple DLLs, multiple multi-phase DLLs, D-SKU DLLs, and PLLs. The heart of the PHY has this PLL that I talked about that creates a really low jitter clock. So one of the problems with a lot of interface IP, and DDR is one of them, is you have to provide a very, very low jitter clock. And you got to get that clock to the DDR5, which is not always easy to do and place and route. For us, whatever, just give us any old clock you got. We're going to filter out all the jitter, no problem. We can create spread spectrum if that's what you want. Not only do you not have to give us a clock, we could actually give you a clock if you want. You could connect this directly to an external crystal, and the DDR5 can actually generate the clock for the rest of the system, which could be helpful depending on how your timing domains are parsed out. The DDR5 looks a lot like a SerDes, kind of more than a PHY. Every pin has its own individual timing and logical resources. So for the read side, everything is constantly tuning itself. So we're constantly looking at the odd and even phases of the data eye and keeping it in the middle. We're looking at the switch point. So in DDR4, you create your own internal reference voltage. So if you have a data eye, if you think about it, if I can draw this with my fingers, if the internal switch point is a little high or a little low, you get duty cycle distortion. So you're eating away your data eye. We're constantly adjusting that. We're looking at you know, positive and negative edges, and we can tell whether they're early or late. And if you think about it pictorially, it will tell you that you can do you'll be able to tell whether it's high or low. So what we believe as the speeds get faster, and also in a lot of areas where you're very cost challenged, that this tuning buys you something. The tuning buys you 5% here, or maybe 7% there, or, you know, being able to tune constantly. You know, at the lower speeds, maybe 15% of the data eye is not a big deal. You got a timing budget. But as we move faster, 15% could be a big deal. And not only could you go faster, maybe it gets you into a cheaper package or a board. And those are things that, if you're a chip provider, if your customer has to buy a more expensive board than your competitor does, that's a really big deal, right? That in that way, he's going to come back and say, look, I got to add 2 layers to the board. That's going to cost me 50 cents. You need to take 50 cents off your chip price. Your gross margin now goes down to the point where your boss fires you. So, you know, those are the kind of things we're trying to do. Again, we also strive to make things easy to integrate. So we use source synchronous signals between the memory controller and the PHY blocks. So source synchronous back and forth. So it allows you to build a really wide PHY, but close timing easily and at a high frequency. So things like having the PLL, things like doing automatic tuning, things to make the integration easy to do. We're trying to make this easy. Typically, in the old days, this used to be one of the most difficult parts of building an entire chip. Many times the DDR was 300-400 pins, so it may have dominated the pins. It's very difficult to close timing. You're typically closing timing late in the process because you typically, you know, people typically keep the I/O ring at the very top of the hierarchy. So, you know, you're doing one of your hardest jobs, one of your least predictable jobs at the very end of the process. So, doesn't make an engineer's life easy when you're missing tape, coming into each meeting and saying, well, it's going to be another week, so we need to push the tape out another week. So those are the things we try to do there, and I think that's basically it. You guys have any questions, comments?
Any questions for Brian?
You want to let him? Yeah, there you go.
So it will generate layout automatically. You mentioned there is a high-level script is there. So
Yeah. So it's you know, think of you know, this is the best way to think about it. Our hard IP looks a lot like soft IP, right? So if any of you guys have used or even designed, you know, a lot of IP, soft IP will have RTL. It'll have some scripting language around it, or maybe use Verilog. So there's many different options, many different ways to do things. If you can include some test bench stuff in the same code, so it looks a lot like that. And then that will just basically, again, we use a version of Magic for layout. So we use a lot of our own tools, as John is probably talking right now, not because we're trying to save money necessarily, but we want to control the tools. And the trouble is, when you use commercial tools, they give you some hooks, but usually the commercial tools, like, no, we're in control. There's a callback, but we're at the top level, and we want to be able to call the tools from a higher level of hierarchy, and it's difficult. It's difficult to get tools like that, and honestly, if you're a tool vendor, it's difficult to support tools. You know, if your tool's not in charge, then the customer can use it in a lot of different weird ways. Did that answer your question?
All right.